hear me fine. Please, if you have any question, interrupt me. I'm going to present my research, but also I hope to talk about kind of the challenges of this area. So I'm going to talk about problems in scientific images, and I believe that many of these problems are beyond or also applying to other media like text. We see a lot of methods for generating text these days. As Jenny said, I'm an associate professor here in Boulder, Colorado. It's very cold, but it's very nice and cozy here inside. So I'm very excited to give you this presentation. So first, I'd like to thank all the people that have helped me. So I wouldn't be able to produce all of this without my students and the funding. So thank you very much. And I'll just jump right in. So I will be talking about image manipulation of all kinds, and I will motivate perhaps this with a very sad and obscure and like really dark episode in science, which is the case of Mercuriani. He claimed that he could implant windpipes in patients who had them removed because of cancer or because of other issues. And he claimed that he could make it so that the patients wouldn't reject the implant if he put stem cells in these implants. It was an amazing claim, and many people tried to reproduce these claims, but one of the main issues that people discovered very early on was the problem with the images. So they discovered, I don't know if you can see my mouse, but they discovered that many of the panels were reused from other panels within the paper. Now, of course, if you've been following Twitter or if you're a regular visitor of PUP here, you see these problems being reported all the time, and that's kind of what I will be focusing on today. Feel free to interrupt me if you have any questions. Now, I'm going to be putting a lot of information, but I hope that because this is being recorded and I hope to share the presentation, you can perhaps come back and see more details. So I'll be talking about several challenges in this field. The first one is image reuse, which is the case that I showed you before. So it's a panel that is taken from somewhere else. Sometimes it's a piece of a panel, sometimes it's a manipulation. So you have a copy, but also some rotation or changes in color so that you're trying to deceive the reviewer. Sometimes it's within the same figure. Sometimes it's within the same paper, so across figures, and sometimes it could be across papers. So there are many challenges there with scale. Another problem that we'll be talking about is manipulation. So this is not necessarily copy, but is rather you're trying to remove or beautify an image. So Western blot, you're trying to remove a gel with Photoshop, for example. Another problem that I think is less studied, but I think could be equally important, is to discover ways that people display data, so they're trying to make the effect sizes appear bigger than they are, and I call this graphical integrity issues. So here, for example, it's a graph where it's trying to show that, let's say, people in Germany work much more than other countries in Europe, but in fact, what's happening is that the way that the graph is being presented is not scaled properly, so you see these massive differences in the bar charts, but the way to properly present this is to start from 0, and then the differences will really appear to be small. So this is called proportional ink issue. And I'll talk about a very recent threat, I think, to us, to people who study research integrity. Is a very real and very scary threat, and I know that many here in the audience are very worried about this. It is synthetic image generation. So there are this amazing new technology where you just put text and you can generate at will images that are completely novel. They've never been generated before, and they look perfectly fine to the human eye. Finally, I'll talk about how to, once we discover these issues, let's say you're a reviewer or you have a tool that does this, how do you present evidence, let's say, in a real case? So I talk a lot with research integrity officers, and many times researchers that are in the middle of these issues say, well, this happened at random. Okay, so how do we generate evidence, like a numerical evidence against those kinds of claims? And I will talk a little bit about that. Okay, so I hope to summarize the talk in case I lose you in the middle of the talk in this slide with the challenges and opportunities. So I have here all the problems that I will be talking about. how easy it is for the authors to produce this, or people that are potentially trying to deceive us, how hard it will be for us or for machines to detect these issues, and what I think are the current, in my opinion, the next steps that we should take. So for image reuse, it's very easy to generate. You just need to copy and paste. It's relatively difficult to detect because because of a scale problem. So we need to detect reuses against all images ever published, and that, in my estimation, could be 1 billion images of scientific papers. So the current challenge, and I'm glad that I think we have some people from STM. I'm glad that we are creating this centralized repository of images, and I think that will be great to make available for companies and for researchers to study. Image manipulation, I think, is a little harder to generate because you need like some knowledge of Photoshop or some tool to make the manipulations in the image. It's very difficult to detect if you want to develop methods because they're intrinsic manipulations. There is not really hard evidence. They're not being reused from somewhere else. And we don't really have methods and standards to do this. So I think that's the challenge. Graphical integrity issues is very easy to produce. You just, we see it all the time in news channels, and it's very easy to just use Excel or something to just start your graph from a specific place. It's very difficult to detect, however, because you need to parse the images. You need to parse the figures, and that's very difficult for machines to do. And there are practically no standards. We have journal standards for graphical integrity, but editors and reviewers are not really trained to do this. Now, in my view, synthetic images could be our biggest threat because they are extremely easy to generate. Once you train a model, it's very easy to generate whatever you want at will, and it's extremely difficult to detect because basically they're training so that a machine cannot detect a fake image from a real image. And the problem is that to create models that can detect these issues, you need huge compute requirements because these models are so big, the ones that generate, that to detect them, you basically need to match that complexity. Finally, for the quantitative evidence gathering that I talk about, I think there are no standards, so I'm trying to work on that. All right, so image reuse, and this is very close to my heart, and I probably spend most of the time on this problem. The way that usually this works, the way that problems are discovered today is through peer review, whistleblowers, the community. But a lot of times these issues are discovered proactively. They're not really done during submission, although we've had some advances on that with some companies creating methods. And myself, I have to disclaim that I've been working this myself with a method and computational techniques. But usually it's retroactive. So how can we make sure that this is being done for every image? And I will talk a little bit about a method that I developed that, to full disclosure, is not. It doesn't work very well, but it's really fast. So I'm trying to develop better methods, and I know there are better methods out there, but the problem is scale. So the way, if a human does this detection, is very slow. It could be inaccurate. It's very prone to errors because it's just very difficult to detect, especially when you're trying to find if there are reuses across images of the same paper, let alone across images across papers. So that's almost impossible. So I'm going to talk a little about our study that is, ancient now. It's 4 years old. We develop a method that is fast and it allows us to detect potential problems in images reuse. We analyze open access publications, and we analyze around 2 million publications from open access. And the dump was from 2015. So now the open access repository is much bigger than this. I think it's 4 times this size. And the idea that we apply a method for media forensics, a very standard method for detecting reuses, and then we pass it through a panel that will say review if maybe the images are being properly cited, so it's an okay reuse, or the technique just lends itself to be reused very commonly. So, and if that's fine, but sometimes we found some problems, some rotation on some claims that obviously were not proper. All right, so I'll quickly go through the methods. So basically, this is again a very standard method. I encourage everybody to read this amazing review. It's 10 years old, but it does a very good job at going through each of the steps that you do for detecting reuses. So this is an image that has reuses, and this is what you want as the final product. You want to have these marks as the reuses. So the way that you do it, you extract some key points, then you match those key points, and then you do some post-processing to remove things that are usually reused in scientific images. All right, so you extract key points. So this is an image it seems fine, but then you have to extract. There are many ways of extracting these key points. You can see in the details in our paper, and then you need to match them. And this is the difficult part, because here we are matching within the same image, but sometimes, but you want to match across all images ever published. And I mentioned before, I believe there are 200 million publications out there, so that probably means we have like 1 billion images. So how do we match pieces of images across these billion images is the challenge, and there are multiple people working on this. And then you want to do some post-processing after that matching and some cleaning up. Okay, so in our research, we did that cleaning up. We presented these matches to our team, so it's just us, the 3 authors of this paper, and we went through the labels and the papers. And this is the summary of those results. So if you are very stringent about whether something might be suspicious, you might say, okay, if 3 reviewers vote that the reuse is fraudulent, if we look at all possible papers, we found around 0.5% of problems in scientific papers. These are usually biomedical papers, so you have to take that into account. But if you only care about biological matches, and maybe you're a little bit less stringent, and you say, well, at least one of the reviewers thought that one of the matches was suspicious, then we're looking at 9%. Okay, so between 0.5% and 9% of the papers, if you will, have some sort of issue. This is in line with other papers that are out there that are done this manually, so we are pretty okay with the results, and the agreement among reviewers is not amazing, but it's decent. Now, the interesting thing that we found is that most of the reuses that we found was across papers. Okay, so that's something that few papers or methods or companies do, because it's just the scale is very difficult. And importantly, we're looking at pieces of images here. So most of the cases that we found are across papers and not within paper. These are some examples, and we have thousands of these cases, and we are still debating what to do with them, either to dump them somewhere or report them. So we found cases within papers, across images, across papers. Sometimes we have copies that are completely verbatim, so almost the same image, just copy in a different paper, but the text is different. So that's what's interesting that we found, just the text being completely different. All right, so I'm going to speed up a little bit here, because these are just, again, some examples that I find interesting. And there are, so we developed a tool called Dr. Figures. It's being currently tried by investigators that do this to prosecute, but there are companies doing this, Image Twin, Proofread, and there are many media forensics tools out there that are free to use. And if you send me an email, I can share those with you. But if you just Google free images analysis, you will find them. All right, so I encourage you to read these recent 2 papers that talk about these image problems and why it's difficult. So there is an entire field called media forensics devoted to this. So the question, many people ask, I mean, if you see Elizabeth Big, I think she has a challenge every time someone says, why can a machine do what you do? Like, she's doing this manually, so many people are like upset almost that she cannot use machine learning. And the challenge is that the scientific images are very special. Okay, so there are many real artifacts in biomedical images that are reuses, but are okay. So you're reusing labels, you're reusing annotations. So that's very different from what usually you use in media forensics. There are many the figures in some of the figures have very low contrast, so there is not really a lot of texture. There is not really a lot of things that you can extract with techniques from computer vision. So that's makes it very challenging. Also, many images appear very similar, but in fact, they're different. And this happened to me all the time when I analyze images and I send emails to authors, say, what's happening here? I don't know the technique, and they say, well, this is exactly what we're looking for. We're looking to generate the same image, but you have to be very, very well versed in the technique. So there is a very high chance of false positives. All right, so image manipulation is another problem, and here I claim that it's much harder because there is no hard evidence. You have someone who is taking an image and manipulating it, but you need like someone who is an expert in the technique. So this case is a Western blot. You need an expert in this technique to understand that these manipulations and the way that it's being manipulated is not okay. So you should detect them. So for the sake of time, I will point you to this paper and explain an attempt that we did. Basically, we're looking at the structure of the noise, and we found that when someone manipulates an image, the structure of the noise in the manipulation area is very different. So we are basically trying to detect an outlier in the noise space, and that's the technique that we developed, and you can see more details of that technique here. It works relatively well if you compare it to methods that are used in media forensics, in traditional media forensics. Well, it works well because we are fitting it to scientific images. So that's why we are trying to add a lot of our understanding of what kind of noises are okay. But it also works well in other data sets that are not in scientific images. And like, for example, these misinformation campaigns that were out there. Okay, so again, more details in the paper. Now, the challenges here, again, is that this is very easy to produce. You just need Photoshop. There are these amazing tools in Photoshop where you can say, okay, paint me, remove things from this area and use things from this other area. But it doesn't copy perfectly. So it does something called a patch match. So it's manipulating things so that the reuses are not immediately obvious, even to computers. And you need an expert to analyze these cases because it's not easy to claim manipulation. Okay, I'll quickly review graphical integrity issues. I think there is a lot of things that we could do. So there are manipulations that we do in graphs that are called graphical integrity problems. I encourage everyone to read this book. It's called Calling BS by Carl Beckstrom and Jevin West. And they go through a series of ways in which people try to lie with graphs. And I think there is a huge area that we could explore with computer techniques. We develop a method to parse specifically graph charts. And so we parse the images and we detect potential problems. And basically, we are trying to detect where bar charts are starting from. And we discover, we analyze hundreds of thousands of images. And we discover around a 5% rate of these proportional ink violations in the images. There are very few standards about this. So if you go into the journals and you see the graphical standards that they have, there is basically nothing. Often there is nothing about the graphical display of information. Synthetic images. I think this is a huge challenge. So I'm sure you've seen this example. So if you go to this website, for example, this person does not exist. You visit the website and automatically generates a completely synthetic person. And the quality of these generations have been increasing dramatically over the last couple of years. Now, the technique they use here is not even state of the art. So this face, although it has like some artifacts, this still looks perfectly fine. And the way that these methods work is that they have this huge, what I call neural networks with millions of parameters, sometimes billions of parameters, and they're able to transform noise into real images. And what's, I guess, scary or interesting, if depending on how you look at it, they're taking these techniques and make it so you input a text, and then it can generate a very high quality image. So here there's a company called Dream Studio where you input a text. So here's a portrait of Zelda, and then there is like they're describing what kind of image they want in natural text, and they put Dream, and it generates this amazing artistic view of that text. Now, of course, there are scientists, I don't know why they're doing this, that are doing applications of this to science. So here you have two examples of this. So in this example, they're generating completely, so these are real images, but they're generating, all of these images are completely novel. They're generated by the machines. And the way that they do it is just they train it on images from the brain in this case, and in this case from X-rays. And this is the thing that is kind of scary, because you can put here, you want a photo of a lung X-ray, and it can generate perfectly fine looking images. But then they say, what if we want to generate an X-ray with a particular disease, for example, and it's able to generate that kind of image. And this is, again, completely novel. There is no way of detecting manipulation. There is no way of detecting reuse. And if you go to this link, you can try it yourself. So you put prompts and it will generate things for yourself. Extremely hard to detect, and there is very few research in this area. Okay, finally, and with this, I hope to finish and make time for the other team. I think we need methods for gathering evidence. So when I talk to research integrity officers that are trying to prosecute researchers, sometimes researchers say, well, this happened at random. And we're developing methods to kind of say, okay, what is the p-value? So kind of what is the statistical probability that if this happened at random, you have these two images that look very similar. And I encourage you to look at this paper. We develop a very simple technique, and you basically get a p-value out of that question. And here's an example. So for example, you have a reuse of something that is like a cell or a microscopy. You will have a p-value that is very small of happening at random. But if you have something like a Western blot gel, well, it's more likely to happen at random because you have much less variability. And if you go even to text, well, it's much more likely to happen at random because people use, the same fonts and things like that. So we try to get at that, but I don't think we have enough methods to do that. Okay, so that was my review of things. I want to invite everybody now to the Computational Research Integrity Conference. We did it last year. I think it was amazing. That's my humble opinion. We have Jennifer there. We have all the many people that are here. I think we have Jana. We have I think I saw Renee somewhere. So it was great, and it will happen next year in May after the Meta Science Conference in May, 11 and 12 in Washington, D.C. I think what we're missing in a lot of these methods is data. So again, I'm really glad that STM is getting many publishers together to create these data sets. And we personally, thanks to ORI, we launched 2 challenges to get this data. These are kind of Kaggle-like challenges so that we get teams to compete and make better methods for computational research integrity. And with that, I'll finish. Thank you so much. This is a summary of the things that I review. I think these are, again, I'm really worried about this last example where we can generate images, but I think we just have so much that we can do in images. But scarily enough, I don't know if you've seen Twitter recently, but ChatGPT and GPT-3 are able to do kind of the same things for text and potential data. So in the future, I won't be surprised if we see completely fake papers coming out of machines with figures, with text, with graphs, with citations even. So thank you so much for the invitation. I'll be happy to take any questions.
Thank you, Daniel. That's an amazing talk and a great summary. I think the slide there is really very helpful. I'm wondering whether anyone has any questions. We've got a couple of minutes. Just put up your hand or jump off mute, I think.
For everyone to drinking now, it's a wonderful social occasion for us. Reasons actually.
I do have a question.
Yes, Jana.
Hello. Hi, Daniel. It's really good to see you again, and thanks for that. That's really interesting, what you've been working on. So we just had the STM masterclass last week in London, where some of the providers of these automated systems, presented their tools, and none of them mentioned even you know, the detection of synthetically generated images, and I think we all agree that this is the huge threat. This is the thing that we're really worried about. At the moment, we're sort of glad if we can find another paper that has very similar looking, say, Western blots, because at least that gives you some kind of indication that you know, they might come from the same source somewhere. But it's you know, I have a lot of, you know, I deal with editors who say this isn't hard proof, this is not good enough. My question to you is, what kind of timescale do you see? Do you think this is going to be that it's realistic to think that there'll be a tool available within, say, the next year that can, you know, detect that, or at least be more helpful than what we have right now?
So are you talking specifically about synthetic images? Yeah.
Yes.
Yeah, this is a problem. I mean, this is so DARPA, so the kind of the funder from the Defense Department here in the US has been funding a program kind of similar about that, because misinformation was a huge issue here in the 2020 election. 2024 election is coming up, so they're worried that, you know, state actors are going to generate lots of things. So they've been working on this for I would say much more difficult problems, and they have developed some methods for detecting synthetic images. I think we should be doing the same for science, but I really worry that it will be that we are, and like the threat is much different from than before, because these tools are extremely easy to use. They're hard to train, so you need like someone who is expert. But once you train it, the way to generate images is very easy. Just use natural text, natural language. And the tools are the methods are extremely sophisticated in the sense that they're trying to fool another machine. So they're trained so that basically they're pinning two machines, one trying to generate images and the other one trying to detect them. And they succeed once they are able to fool the other machine. And those machines are usually very sophisticated. So you need a lot of compute. In principle, you will need a bigger model, more computational power. I think it's possible. I think it's possible if we are ahead of the curve. These methods are appearing every day. So if we somehow try to get ahead of what's happening, be on top of things, it will be just a game of cat and mouse, in my view. There are methods for detecting this that haven't been applied to these kinds of issues, and we hope to develop something ourselves and make it available in Dr. Figures, which was not that great. I mean, the feedback that we got, even for the things that imagery used, was pretty bad. But we hope to add that. But I'm very pessimistic. I guess to sum up, I'm very pessimistic about if we will be able to detect these issues. And this applies to text and to other things. Yeah.
Okay, thank you, Daniel. That's yeah, interesting. I don't know. I think the pessimism is real, but I kind of think our protection could potentially be expertise from scientists, because it's still possible that these tools can generate things that look good, but from an expertise point of view are not plausible. But I think in the interest of time, we'll move to our next two speakers. So we have a duo to talk to us from France. So Guillaume Cabanac and Cyril Labbe. I'm very pleased to announce that they are both now professors at their university. So we have Guillaume coming from the University of Toulouse and Cyril coming from the University of Grenoble. Yes, so congratulations on your promotions, and we're very much looking forward to hearing about the problematic paper screener that you've developed. Thank you. I think you're still on mute. There we go.
Sorry, excuse me. So yeah, I'm going to start the presentation, and so this is a joint work with Guillaume and Alexander Magazinov from Yandex in Russia, and it's about the detection of. So we are working on text, and mostly we will present the problematic paper screener, and you can see it as a database of strange papers, suspect, erroneous, or fraudulent. And the aim of the probability paper screener is to try to crowdsource the post-publication reassessment of this paper. So we are listing suspicious paper, and we want people to help us to flag them on PubPeer, for example. So Guillaume, maybe you can switch. Yeah. So I will start with a quiz. So maybe you could use the chat. Are you able to tell what counterfeit consciousness mean, or what man-made brain power mean? So some of you, I guess, have already heard that kind of thing. And it is artificial intelligence. And we can see a lot of papers that are using these words instead of artificial intelligence. And sun-oriented force will be solar energy, and pinnacle flag to clamor proportion. You can try to use the acronym to understand that this is peak signal to noise ratio. And so you've got some more after that. So credulous Bayes would be naive Bayes, which is a very well-known classification scheme in artificial intelligence. And so if someone is using credulous Bayes, it's completely meaningless, and no one will understand it. So boson malignancy or boson peril will be breast cancer, and then often, so another one. And so you have to understand that all these strange wordings has been picked up in real paper that were published by a real publisher, not predatory publishers. And so we collected, and Alexander Magazinov collected a lot of them. So you can see in the next slide the list. So on the left-hand side, we've got a list of tortured phrases, and on the right-hand side, you will have the real wording. So, for example, profound neural organization will be deep neural networks. And so we found really plenty of paper having this strange wording, and so that's why we wrote we wrote this preprint about tortured phrases. It's an open call for investigation because we explain the problem, and we try to measure the importance of this presence of tortured phrases, and try to see where this kind of thing could be detected. And we think, and we are quite sure now, that the source of these tortured phrases are paraphrasing tool, and a particular one that is called Spinboat. And this tool aims to rephrase, or at least to substitute words by synonyms. And this is used to evade or to plagiarism, so that plagiarism will not be detected. So you just take a piece of text, try to rephrase, or even not to replace words by synonyms, and then you just pass that in your new paper. And so there is even so the services can be they are making money with it, because you have to buy credits, so to use the paraphrasing service. So this is quite old technology, and now people are doing well. You know that with text we can do things that are really better than that. Daniel just mentioned the GPT-3 and Chat GPT that has been quite doing some buzz these days, and so you could now try to use this kind of tools to generate some text. And so so there are all these paper in the field, and we need to do something.
Yeah, we saw the field, so science as a beach, and we wanted to eliminate these pollution. So we want to depollute the scientific literature. And our method is really basic. There is no rocket science here. We described it in this JASIS paper. It is based on fingerprints because we use the crime scene metaphor. So in a paper, you can find such tortured phrases, and we view them as fingerprints, and we instruct our informant, the problematic paper screener, to find these fingerprints in the literature. So for instance, here, instead of created nations, we should have seen developed countries, you see. So basically what we do, we are not able to analyze, parse, index the entire literature, more than 120 million papers. So we let dimensions do that. That's a company that indexes the literature and allows researchers or customers to use their search engine and their API to query this big corpus. That's what we did by designing very simple queries like that, where we query dimensions for each and every fingerprints that we humans listed. And basically, it runs every night. The problematic paper screener screens the 120 million papers using dimensions. And when we have a paper that is matched by multiple fingerprints, that's a candidate for reassessment. So the more fingerprints a paper contains, the more interesting it is to be reassessed and maybe corrected or even retracted. That's what we want to do eventually. So since we found many papers with errors and those fingerprints, those tortured phrases, we had to keep a list of them. And we believe that it would be good for the public to know about that. That's why we developed the problematic paper screener. That's an online website that is public, and that shows that some papers, like this one, contain a lot of tortured phrases. So here, 20 tips. Again, that's the metaphor with the person that would say to the police that there is something wrong with this paper. And then every day we find these papers and we review. When I say we, it's us at the problematic paper screener and the entire community that uses PubPeer a lot. And that's why we added this column. When a paper is posted on PubPeer, then a link to the PubPeer post appears here. Many papers are not reassessed yet, and there is a special place where you can find these invitations for human assessors. So we invite the people to reassess the papers and post on PubPeer with some templates that the PPS is able to provide. And the people also find new phrases. For instance, in areas where we are not expert, in microbiology, for biology, for instance, some people are able to find new tortured phrases, and we review PubPeer every day to extract these new phrases and add them to the PPS so that tomorrow we'll be able to screen the literature for these new deviant ways of expressing things. So it's a snowballing effect that we comment here, and a form of crowdsourcing of human reassessments that we perform using the problematic paper screener. Here is an example of a comment that I did a few days ago, and you can see that we don't incriminate, we only ask questions, and we provide evidence for the problems that we found. It's really important that what the program has found is is checked by the human. So for instance, instead of ascorbic corrosive, it should be ascorbic acid, or glucose bigotry, it should be glucose intolerance. And sometimes we have authors replying, or publishers who then retract papers and post on PubPeer, and we invite really the publishers to do that. It's really important for the community. Thanks to PubPeer, we were able to find and meet other scientific sleuths like Elizabeth Beek, Nick Wise, or other people who are anonymous on PubPeer. Now we form a group and we meet from time to time. We are very active, we exchange tips and so on. And on PubPeer now we have plenty of notices of records of problems in papers. Cyril?
Yes, and this is statistics about the places where the venue where the most where there is a concentration of tortured traces. So you can see that they are quite spread everywhere, even in high-profile publishers. And you can see also the trend growing very fast. And so we can guess from that graph that the technology used by the spin boat is started around the mid 2015 or something like that. And our preprint was in 2001, so that we hope that the bar in 2022 will be less high than the previous one. Hopefully, publisher would be aware of that kind of problem and maybe succeed to succeed to not publish this kind of strange paper. And there are other panel in the PPS, so it's not only about tortured phrases. There are also 3 sections about the detection of completely generated text using context-free grammar, probabilistic context-free grammar. So these are really old technology of text generation. And so we have an example just after this slide, and it's a paper generated by MatGen. So here all the text is completely, only the figure is not generated. All the rest is completely randomly generated. And this one was published by Springer Nature. And so it's quite easy to detect, and there are several ways to detect that. So what we did with Guillaume is to extract what we call the fingerprints. So the kind of chunk of sentences that are really characteristic from these generators, and we are using that to detect them. And yeah, next slide. And so there are also other sections that are related, for example, the Seek-and-Black's tool and the problematic cell lines detection are related to scientific error, let's say, or things that are completely erroneous. So it's not about things that are generated, it's about trying to spot errors in the papers. And so you can also use this kind of papers. So if a paper is erroneous, the paper that cites this erroneous paper may be also erroneous. And so that the feet of clay parts of the PPS. Maybe you want to add something about that, Guillaume.
Yeah, the picture to look at it is this one. We want to flag those papers that contain in their references papers that are deemed to be unreliable according to the PPS and sometimes confirmed on PubPeer. And we believe it's very important to make sure that the literature is made of very robust bricks of knowledge, and we need to reassess those papers citing disputed knowledge. a few more statistics and also a tweet, because I've been tweeting for more than a year about these problems, and it's sad, but it's true. Sometimes retractions come after a stress and effect on Twitter. So publishers react when they see that the community is discussing a lot online. And what I would like is a more proactive attitude of the publishers. I would like them, for instance, to monitor per peer. There are tools for that, and that would be very much more effective. Well, we found that there are 3 papers every 10,000 papers that contain tortured phrases in 2021. Regarding the affiliations, India comes first and then China. We need a caveat here. Most of the research in these countries is of top quality, of course. So we shouldn't over generalize these findings, but yet. Then on the problematic paper screener, you can find 10K papers that contain tortured phrases. They are not published by the predators. It's the elite publishing industry, the top, yeah. You can see the names here, and we need help from the community because many papers are marked as invitation for human assessors. If these papers weren't at all cited, maybe it wouldn't be such a problem, but we found that these papers are cited, and there are sometimes some kinds of citation hacking occurring, and it's well documented on PubPeer and some in other places. So now we are at the conclusion of our talk. Our main message is we must decontaminate the scientific literature. We've been talking about some actors like scammers, but even in the medieval times, you had scammers. The new thing maybe is that the gatekeepers that need to protect science are failing at their task because they accept these papers. Publishers, I believe, are not monitoring their products so well, and policymakers are promoting publish or perish, which is really bad. The motives are promotion, recognition, or symbolic capital. When you look at the fraudsters, they use many things here. We only spoke about plagiarism, but there are other issues. The consequences are very dire, the pollution of the literature, and when you hear that AI is able to synthesize the literature, I'm a bit scary because garbage in and garbage out. And also the trust that society places in science is a bit eroded, which is really bad. I told you about detectives. There are professionals like Cyril and myself and many others. And there are also hobbyists, people who prefer to post on PubPeer compared to doing some puzzles, for instance. We know some of these people. We are volunteers and we contribute pro bono these skills. Our aim is to curate the literature, to decontaminate what has been published, and we need also to take care of the new manipulations that will occur, and we have started talking about that in the previous talk. Our way of handling the problems had been to create the problematic paper screener for decentralized reassessment of the literature, and it helps people focusing their attention on 10K paper instead of 120 million papers that have been published. So thank you for your attention.
Thank you both. That was an amazing talk, and I think a great example of what can be citizen science, because these kinds of tortured phrases are quite obvious, in many instances, and it is interesting how many times they must be being missed during the production of publications. Many people are not seeing these phrases when they're actually there and quite clear. I'm wondering whether anyone has any questions. Please